Hello, and welcome to this edition of the CSIAC podcast series. This episode will examine the infrastructure deployment pipeline workflow and assess the risk that this may impose upon an operational system. In this podcast, a generalized infrastructure deployment pipeline, IDP, reference architecture will be presented to assist with risk assessment and mitigation. While the NIST Cybersecurity Framework, CSF, largely mitigates IDP risks, additional controls are still required to fully assure cybersecurity for the continuous deployment CD process. We'll describe the benefits of infrastructure as code, IAC, and how to leverage the capabilities in support of DevOps, Development Operations Initiatives. IAC is an emerging concept for automating the provisioning of infrastructure services and for managing infrastructure platforms. We'll also describe prior research studies that have addressed cybersecurity topics relating to both IAC and IDP. There are several research studies that have addressed cybersecurity topics relating to IAC and IDP. The article, "Where Are the Gaps?" was the impetus for IDP cybersecurity research. It identified the lack of academic research in the area of IAC cybersecurity practices and standards. The article, "Security Support in Continuous Deployment Pipeline," focused on the specific topic of CD pipeline security. The article, "Securing a Deployment Pipeline," took a systems engineering approach to securing the CDP. And NIST's Framework for Improving Critical Infrastructure Cybersecurity provided a hardening framework that could be used to address the specific cybersecurity vulnerabilities posed by an IDP workflow on the operational system. There appears to be an area between the deployment pipeline and the operational system that represented a gap in the current research. There are two primary questions that need to be addressed. First, what is the IDP workflow risk created by an identified vulnerability? Second, does the IDP workflow represent an insider threat to the operational system? A generalized IDP reference architecture provides context for the risk assessment. The research data collection is constrained by the IDP system reference architecture, the age of the data, and the data source. This reference architecture was chosen because it represents the operational system viewpoint of the IDP workflow and is based on previously reviewed academic research. In addition to the reference architecture, a binary repository and continuous deployment service were added to represent an IDP lifecycle, as shown in the figure below. In the research paper, "Security Support in Continuous Deployment Pipeline," a notional set of tools was defined that fulfilled each of the reference model capabilities. The tool vulnerabilities selected for research fulfilled the requirements of each component in the reference architecture. The NIST Cybersecurity Framework reference architecture was used for this research. The CSF prescribes controls through information references. The references specify sections of standards, guidelines, and practices documented in other NIST publications. For this research, the NIST SP 800-53 Revision 4 information references were used. These controls map directly to the CSF core requirements. The research population is the group of all cybersecurity vulnerabilities. A cybersecurity vulnerability is a defect in an information system that leaves the system open to an attack vector. To be authoritatively recognized as a member of this population, the Common Vulnerability and Exposure CVE database maintained by the MITRE Corporation was utilized. It contains only vulnerabilities that are less than 5 years old. The vulnerability must be relevant to the IDP workflow or deployable artifacts. In order to assess the magnitude of the risk for each of the selected CVE records, the National Vulnerability Database was queried using the CVE number. The identified vulnerabilities are grouped according to threat vectors. The confidentiality, integrity, and availability CIA impact on the IDP workflow and operational system is analyzed for each identified risk. Threat impact is defined by the exposure factor, EF, and is stated as a percentage of the change in the operational CIA security posture. The EF provides a construct for quantifying the impact of the threat vector on the operational system. The EF value is a subjective percentage of the operational asset lost due to the impact of the vulnerability. The EF is used to calculate the single loss expectancy value, which is calculated as the asset value multiplied by the EF. The vulnerabilities and associated risks were mapped to common cybersecurity threat vectors. The results of the threat vector analysis show that the vulnerabilities tend to be grouped around a small number of threat vectors. The data sample provides multiple examples of each type of threat vector. An analysis of the vulnerabilities indicates that the vulnerability likelihood remain the same for the IDP workflow and the SLE. This is because the complexity and privilege requirements remain the same, independent of where the attack is targeted, but the impact of the attack is different depending on the asset target. Though there is not a statistical correlation, there is an interdependence between the risks. The IDP workflow vulnerability must be realized for the SLE attack vector to be realized. The application of the cybersecurity controls does mitigate the IDP workflow cybersecurity risks. The application of the cybersecurity controls requires several key architectural patterns for mitigating the threat vectors. To prevent the introduction of malicious code, all deployable artifacts must be built from a version-controlled source code repository. The IDP must require multiple levels of access. Development, test, and operational deployment should require different permissions. Authentication and authorization should be managed at the enterprise level with consistent policy and training enforced. Elevated privileges must be managed at the enterprise level. The IDP should be isolated within the operational system to prevent denial of service attacks. The identified threat vectors present an asymmetrical threat to the operational system. There are three main defect types that define defective scripts, which are file system operations, infrastructure provisioning, and user account management for an IDP workflow. The research results conclude that the application of the CSF controls does largely mitigate the IDP workflow cybersecurity risks, but a partially unmitigated threat vector remains for the operational system. Many of the IDP workflow vulnerabilities present an asymmetrical threat to the operational system. The CSF and NIST SP 800-53 controls must be evaluated specifically for each IDP workflow, and the operational system. Additional cybersecurity controls may be required to adequately address the cybersecurity threats posed by the IDP workflow. These include additional separation of duties and least privilege access controls. Secure coding standards specific to the infrastructure code need to be developed. On behalf of the CSIAC, we would like to thank you for viewing this podcast. We hope you found the content useful and informative. If you would like to provide feedback or comments, please visit our website at www.csiac.org, where you can also find additional content to review. Thank you.
Did you know that CSIAC offers free monthly webinars featuring experts in the areas of cybersecurity, software engineering, modeling and simulation, and knowledge management? Come see leading industry professionals talk about industry practices and leading research. Make sure to visit www.csiac.org/webinars in order to subscribe to our mailing list and see when the next webinar series is available. There you can also watch previous webinar series to catch up. Visit www.csiac.org/webinars.